but I don't see any real physics. I want acceleration and I want friction. As with every web development project, by default our codebase is not responsive. If we want to make sure the effect scales up and down to fill all available space when we resize the browser window, we can write that logic ourselves. It's simple. I want to keep object-oriented code structure, so down here on my effect class I create a custom method I call, for example, resize. It will take the new width and height as arguments. I need to update some of these properties on the effect class when the resize event fires. I need to update width and height of the actual canvas element to these new sizes. Then I set width and height properties we have on our effect class to these new updated values. We know that when an instance of a class is created, all the code inside is executed. I will take advantage of that and I will put some extra code in here, some code that I want to run at the point when effect is created. We are already doing that with createParticles method. I also want to add event listener for resize event here. We are inside of a class here, so important thing is to either bind this callback function or I can use ES6 arrow function in here. Using a regular callback function will give us an error if we plan to use this keyword inside this event listener. I want this keyword, when used inside this code block, this event listener, to point to this effect object. ES6 arrow functions were created to simplify function scope, and one of their special features is that they automatically inherit this keyword from the parent scope, which is exactly what we need here. I will console log this auto-generated event object here. Now, when I resize my browser window, event is firing and we can see the object here. Inside, I'm looking for the new updated width and height. I find them in here. So we access it like this, e.target.window.innerWidth. Now, when I resize horizontally, we can see it's updating. I know that our custom resize event expects width and height, so when I call it here, I pass it the new updated width and the new updated height. When I resize the window, I can see that canvas size is changing as well. One thing we have to remember when working with canvas is that resize event resets canvas state to default values, so I have to redeclare fill style in here every time it runs. We are inside of a class, so I want to use context instead, and I guess it will be expected here in a constructor. It will be converted to a class property. Now I use this ctx variable and I pass it to the class constructor here. I actually delete this and I use this.context here. Okay, let's say I want to keep this gradient fill even when we resize. I need to copy this entire code block and I put it here inside the resize method, because when canvas width and height changes, I need to recalculate the direction and the breakpoints of the gradient to make sure it covers the new resized canvas area. I will use this.context here, here, and here. And I pass the new updated canvas width and canvas height to createLinearGradient method. I can also use the updated width and height properties. When we make canvas larger, we are giving particles more space to spread around. This would be fine, but when I make canvas smaller, the way we make particles bounce off the edges, we are running a risk of trapping some particles outside the canvas area. We can rewrite the movement logic in particle update method and make them seek middle of canvas, I guess. Or even simpler, every time resize method runs, I will run a custom reset method on particle class, which will redistribute them only within the newly available area, making sure that no particles get stuck outside the canvas. I only run this after we resized and updated all properties. For each particle object inside particles array, call their custom reset method we just defined. Now, when we resize canvas, particles always reset to fit into the newly available larger or smaller effect area. Remember that canvas state always resets to default when canvas is resized, which includes fill style and stroke style resetting to the default black color. That's why we have to redeclare our colors inside our custom resize event. I want the particles to react to mouse. I will create a custom mouse object as a property on the main effect class. Initially, I set x and y coordinates of the mouse to 0, 0. We will also keep track of whether mouse button is pressed down or not. We will also have a radius around the mouse, an area around the mouse within which the particles react to it. We can think about it as a mouse influence area. I create another event listener here. I copy it 2 more times. We will listen for mouse move, mouse down, and mouse up events. I put a console log inside mouse move event and I will log that auto-generated event object, just to see what kind of information about the mouse event we can get. As I move mouse over canvas, mouse move event is triggering and mouse event object is being generated. I open it. Here I can see x and y coordinates where the cursor is. Perfect. I want to make sure these mouse coordinates are available all over my codebase, not just inside this callback function on event listener. So I will assign them to x and y properties on my custom mouse object. I can delete this console log. I only want mouse interactions to happen when mouse button is pressed down. Only if pressed property from line 56 is true. I have to use this dot here and here. Okay. When mouse down event fires, we set mouse pressed to true. On mouse up, we set it to false. On mouse down, I will also update current x and y coordinates, like this. I console log mouse x and mouse y to see if it works, if these values are being assigned to our custom mouse object correctly. Yes, that works. I will handle mouse interactions inside update method on particle class. I say if this.effect.mouse, this.effect reference is here on line 17, and through that we are accessing mouse object from line 55. Pressed property here on line 58. If that is true, we want to calculate the distance between this particle object and the mouse. Again, we want to calculate the distance between 2 points in a 2D space, this time between particle and mouse. We calculate dx, the distance between the particle and the mouse on the horizontal x-axis, dy, the distance between them on the vertical y-axis. We have 2 sides of an imaginary right triangle. To calculate the distance between these 2 points, we need to know the length of hypotenuse, the longest side of the right triangle, opposite to the right angle. We can use Pythagoras theorem formula, which would be square root of dx squared plus dy squared. Or we can use built-in math.hypotenuse method, since we are in JavaScript environment. When mouse is pressed, we calculate the distance between mouse and particle. If the distance is less than mouse radius, I want to calculate the angle between mouse and particle, so I know which way I want to push the particle. I want to push it away from the mouse, and that could be in any direction, depending where mouse and particle currently sit relative in relation to each other. I calculate that angle between them using math.atan2 method. Notice I have to pass it dy first and dx second. Math.atan2 gives us the counterclockwise angle in radians between positive x-axis and a line projected from point 0, 0 towards specific x and y coordinates. It gives us this angle. The resulting values are laid out differently if you use particle first or mouse first when calculating dx and dy, but it doesn't matter because we can adjust our code to whatever values it's given us. Basically, we use math.atan2 to give us a sense of direction. Whatever the result is, we can work with it to make it do whatever we need it to do. Let me show you. Let's see how it works in this particular code base. So we are getting a range of values between 0 and plus pi, so half circle, and then 0 and minus pi, another half circle. This single angle value that math.atan2 is returning is all we need to be able to push the other object, in this case the particle, in the correct direction away from the mouse. We do that by increasing x by cosine of that angle value and y by sine of that same angle value. Now, when I click somewhere and I hold mouse button down, we are pushing particles away from the mouse in linear speed. Combining sine and cosine and passing the same angle will make the particles move away in a circle like this. Try to swap sine and cosine, use both sine, both cosine. It should hopefully help you understand better how these values affect particle motion. Trigonometry is complicated for beginners, so don't worry about it too much. That speed is consistent because sine and cosine convert any angle value we pass to it in radians into a range between -1 and +1, and when x and y coordinates are increased by that small value for every animation frame, it results in particle moving by that value for every animation frame. Step by step. Particles move at the same speed away from the mouse until they reach the radius of the mouse, and at that point, the distance is no longer more than mouse radius value, so they stop moving. We can introduce some physics and make their speed relative to the current distance between particle and mouse. I want them to move fast when close to the mouse and slower as they reach the edge of mouse radius. When they move outside the mouse influence area, they will completely stop. That force is the ratio between maximum distance, so mouse radius, and the current distance. We will apply this a little bit later. Before we do that, notice how when the particles are at the max range, they kinda move around the mouse in circles, sliding along the outer radius of the interaction area. Nice. Now that particles react to mouse, it is possible to push them outside of canvas area, and once we push them all the way outside, they will get stuck there. We want to prevent that. This code block makes particles bounce from the edges of canvas. We need to make some changes to it. Let's comment out all this code. I'm still animating, which I can confirm by holding down mouse button. The particles will still animate and react to that. If I do this, particles will just move off screen. They will not bounce when they hit the edges of canvas anymore. I say if the horizontal position of the particle is less than this dot radius, which means the particle circle is touching the left edge of canvas, make sure it can't go any further left. If it was pushed further left by a large force, it doesn't matter because we will set it back to that position exactly on the edge, and we will flip its Vx to the opposite value, making it bounce and making it travel to the right. As you can see, after doing this, we can no longer use mouse to push particles outside of canvas here on the left edge. Let's do the same thing for the right edge. I can use else if here because particles can't be both close to the left and the right edge at the same time in the same animation frame. Else if horizontal position is more than width of canvas minus radius of the particle, meaning that the right edge of particle circle is touching the right edge of canvas, we make sure it can't move any further right, and we flip its horizontal speed to its opposite value, making it bounce and move to the left. If I try to push particles on the right edge here, I see they can't be pushed outside of canvas anymore. Nice. I want to do the same thing for top and bottom edge of canvas, so I copy this code block. It will be another else if, this time covering the vertical movement. If y is more than radius, y is equal to radius, and we flip velocity y to make it bounce and move down. If y is touching or is below the bottom edge, we make sure it can't get any lower than that, and we flip Vy, making it move back upwards. I tested by trying to push particles outside of canvas on all 4 edges. I increase the radius. Let's do 300. Be careful with the number of particles. Increasing the number of particles will exponentially increase how performance demanding our codebase is. Same with max distance. If I increase max distance, we are connecting more particles, drawing more lines, and at some point you will notice it starts affecting frame rate. There are many more ways to optimize this codebase and make the animation very smooth even on the oldest computers. I will cover some of those more advanced optimization techniques in a future class. I want to really test that it's impossible to push particles outside of canvas, so I increase mouse influence radius to 350 pixels. I am squeezing them against the edges of canvas, but as you can see, they don't get stuck or pushed outside the boundaries. Perfect. I can set mouse radius back to 150 pixels. I want to change the color of the gradient. I change it down here inside the resize event listener. White, gold, orange, red. And also up here on the first page load. Whenever we make any changes to the gradient, the way I structured this code, we need to always change it in these 2 places, unless I decide to refactor this later. Particles move away from the mouse in linear, consistent speed. I want particles to have some physics. Here I am calculating force. Currently, it's a ratio between mouse radius, the area around the mouse within which particles react to it, area within which I want particles to be pushed away from the mouse, and the current distance. I can use that force value here and here to actually influence particle motion. But when I try it, I see that it still doesn't do any impressive physics. We will have to refactor this formula a little bit. If I increase mouse radius, I can see particles can't be pushed outside of canvas area. But I don't see any real physics. I want acceleration and I want friction. I set particle radius, the size of all particles, to be 2 pixels up here. I will make particles move very fast when they are close to the mouse. They will get a big push. I want them to move slowly if they are close to the outer radius of mouse influence area. This is one simple way how to implement it. I will name my variables in a way so that it's easy to understand what they do. I will need 2 separate speed values basically. Vx and Vy, horizontal and vertical velocity values, create the bouncing ball motion that flips when particles hit the edges of canvas area. I don't want to be interfering with how that works, so I create a separate set of variables for speed of horizontal push, push x, and vertical push, push y. The force of this push will be determined by how far the particle is from the mouse when we click or when we move the mouse around. Now we have 2 forces influencing particle motion, the bouncing motion from Vx and Vy, and mouse push force from push x and push y properties. I have to adjust my code with this in mind. Instead of updating x and y positions of the particle in here, I will calculate that push force here only, like this. I delete this entire code block, we don't need this anymore. Let's clean up after ourselves. Right now, particles just bounce around because of lines 58 and 59. I want the push force to also have influence on the current particle position, so I include it in this formula, like this. Okay, horizontal push is strong. Let's do vertical. Right, they fly off fast. In the real world, when you push something, there is a force called friction. Friction works in the direction opposite to the direction in which the object is trying to move, and it gradually slows the moving object down. To simulate the force of friction in our simple virtual physics project, I will create it here as a property. It could also be general property on the effect class if I decide that all particles are subject to the same friction force. Placing it here on each particle object individually allows me to give each particle a different friction value. Maybe heavy particles with larger radius have a different friction value than small, light particles. For now, I set friction for all particles to be 0.95. As we push the particles with mouse, I want them to move fast, but for each animation frame, I want the force of that push to diminish until it reaches a value close to 0. At that point, the bounce in motion will be stronger and it will take over because we are including Vx here. I'm taking the force of the push, and for each animation frame, I'm multiplying it times 0.95, basically reducing the push force by 5% for each animation frame. I do the same thing for vertical position. Now we have physics. To make sure I don't push particles outside of canvas, I will actually cut these 2 lines of code and I will paste them up here. As you can see, the order in which we run these checks for each animation frame matters. Radius of the particles will be a random value between 1 and 11 pixels. I wrap it in math.floor for performance reasons. It's always easier for JavaScript to work with integers in our drawing code, so I always advise to use math.floor for all speeds and sizes if the effect you are trying to achieve allows it. I click somewhere to push the particles. If you look closely, you will see that particles that were close to the mouse when the click happened get pushed by a much larger force than particles that were closer to the edges of the mouse interaction area. We can tweak how fast the particles slow down by adjusting the friction value. Now I'm saying slow down the push force by 30% per animation frame. I can also slow them down only by 1% per animation loop. Friction number has to be less than 1, because if you keep multiplying the force by a value larger than 1, it will get faster and faster as the animation runs. In that case, I would just push once and particles would keep getting faster and faster endlessly, which is not what we want. I think 0.95 is a sweet spot, but as I said, you can also make friction relative to the radius of each particle for even more realistic effect. I change mouse radius to 200. Try to push them around, adjust friction values, and see how the particles react. We can turn this into many completely different and beautiful animations. If you want to take this even further with me, create a copy of this project folder and all the files at this stage, because I will write code for multiple variations, some simple, some complex. But I will always start each variation from this point. This is the final project, and I will create multiple experimental branches, all starting from here. Let's go.